Never mind the philosophy, never mind anything of this kind, just get the equations. The problem is only to compute their answers so that they agree with experiment, and is not necessary to have a philosophy or argue or worries about the equation.
What he really means by philosophies here is physical meaning behind the equations. They're just mental shortcuts. They're just these shorthands to help you remember which calculation to make at what time. No, this is a complete reversal. The purpose of scientific knowledge is to first understand the cause and effect relationships, and math only comes in to elaborate on the properties of those cause and effect relationships. You need to understand what cause and effect relationships you're even talking about before the math means anything. And this is, if you've ever been in a physics class and just thought like, oh my god, this is just a bunch of math that doesn't mean anything. That is just an enormous tragedy that comes from this way of viewing physics, is that it's now taught in a way, physics is now taught in a way that is unphysical. In his lecture series on the character of physical law, Richard Feynman lets us in on a lot of his scientific process. We understand in this lecture a lot of the ways he comes at science, a lot of the ways that he thinks about the physical world. And what I have found through watching this very engaging lecture is that the lecture is a treasure trove of the different ways modern physicists are confused. It's as though Feynman was extremely influential. Now, I don't know if Feynman was actually influential, but he certainly is a popular physicist, and for good reason, because he's such a cool guy, such a character. He lived his life in such an independent, first-handed kind of way with his own personal values. I mean, he is a personal hero of mine in certain ways. But when it comes to his actual approach to physics, at least as it's witnessed in this lecture and a lot of the other things he said, we can see that he represents a lot of what is wrong, a lot of what is off track about modern physics. And arguing against a lot of the points that he makes in this lecture is going to be a great opportunity for Inductica to present the way that we think about the physical world and the way we think about the scientific method. So joining me here is, I don't know how to pronounce your last name. How do I pronounce your last name?
The first one.
Aviram Rosochotsky.
Something like that.
Yeah, I like it. You're always something like that. You don't even bother trying to get me to say it right. All right, so joining me is Aviram Rosochotsky. He's a friend of Inductica. Aviram is a philosophy graduate student at Tel Aviv University doing research in the philosophy of physics. Welcome, Aviram.
Thanks, and thanks for inviting me, James. I agree with you that these Feynman lectures are very influential, and in a sense, the ideas here are still prevalent. So I think that the commentary about them will be valuable for many people interested in these issues.
Awesome. Well, let's get right into it. So let's listen to a first clip of Feynman, and we'll be giving our reactions.
This shows, again, that mathematics is a deep way of expressing nature, and attempts to express nature in philosophical principles or in seat-of-the-pants mechanical feelings is not an efficient way. I must say that there is possible, and I've often made the hypothesis, that physics ultimately will not require a mathematical statement, that the machinery ultimately will be revealed, just a prejudice like one of these other prejudices. It always bothers me that in spite of all this local business, what goes on in a tiny, no matter how tiny a region of space, no matter how tiny a region of time, according to the laws as we understand them today, takes a computing machine an infinite number of logical operations to figure out. Now, how can all that be going on in that tiny space? Why should it take an infinite amount of logic to figure out what one stinky tiny bit of space-time is going to do? And so I made a hypothesis often that the laws are going to turn out to be, in the end, simple like the checkerboard, and that all the complexity is from size. But that is of the same nature as the other speculations that other people make. It says, I like it, you don't like it. It's not good to be too prejudiced about this thing.
All right, it's not good to be prejudiced about the idea that any one part of space or any one part of the ether has some kind of finite nature and some finite number of things are going on in that location, that's just a prejudice. So some background for anyone who's a little confused by this. He's referring to quantum field theory, which effectively gives an estimation procedure for the state of a quantum field at any one location, and that estimation procedure is an infinite series, which of course can't actually be finished, but you can approximate it by finishing part of that infinite series of terms. You can approximate what is happening quantumly at that location. And Feynman is saying, well, I'm biased. Maybe, I don't think there's actually an infinite number of things going on at each location. But that's just a bias. Maybe, really, at the end of the day, all there is mathematics. So I picked this first because this really shows right off the bat that Feynman represents one of the things that's wrong with modern physics is that it's unphysical, and that might sound a little bit crazy to say, like I'm being over dramatic, but this is truly unphysical thinking. The idea that there might be an infinite number of things, a truly infinite number of things happening at every location, you are simply not using basic physical reasoning in order to understand what it is you're dealing with, in favor of simply accepting some mathematical framework and saying, oh, well, math seems to work at getting correct predictions, so maybe that's all there is. This is equivalent to Feynman telling Copernicus, like, oh, well, I understand that you have this simpler theory, and it might be right, and I certainly like it more. I like your simple theory where that it accounts for, retrograde motion with the planets going around the sun instead of around the Earth. But maybe epicycles are true, and maybe there's an actual infinite number of epicycles. Maybe the planets follow an infinite number of circles upon circles upon circles as they spiral around the Earth. For all we know, that's what's actually going on. Comments on this, Aviram?
Yes, I have a slightly different interpretation of what's going on here. I think that Feynman is trying to think about continuous things, like continuous processes and continuous fields, and he thinks of it like Zeno. He thinks of it like you have a continuum. It is composed of incountably, infinitely many points, and as a consequence, he arrives at the conclusion that if you assume fields, then you have infinitely many locations of activity, an infinite amount of activity going on in all of these points. But I think that one way of solving this is by actually getting to what is originally a point by Aristotle. When you decompose a continuum, you can only truly decompose it into smaller continua and the boundaries between them. So if you have a portion of the universe where there's field activity, you can subdivide it into smaller portions, but those portions are going to be of finite numbers. So in a sense, you will only be analyzing the field with finite parts of the region where these activities are happening. So you are never really dealing with infinitely many points undergoing infinitely many processes. And Feynman doesn't really hint at this solution, so he's trying to...
Yeah, but Feynman's, he's unaware of all of that. Yeah, sorry.
So he's trying to solve the problem by physical means. Instead of conceptually analyzing the problematic idea there, he says, well, I can avoid this paradox of infinite points with infinite activity by saying, no, there are no true continua. Everything is discrete, and the number of vertices in this discrete lattice or in this discrete distribution of points is finite, and so I have no problem with infinite processes. And this reveals something about his kind of Zenonist or atomist way of thinking. And I don't know if you noticed that, but when he speaks about Maxwell's laws and the law of universal gravitation, he seems to be saying that there is some way in which these laws are unsatisfying. So the law of gravity, Newton's inverse square law, tells you what the force is, but it doesn't really tell you what's exerting it, how it is being exerted. And Maxwell's equations also, he thinks of them as, in a sense, you don't really know what's going on there. You're not.
Yeah.
You don't really get in any insight.
And he's right about that. He's right. This is his better half. This is his, like, Feynman's spirit is better than his philosophy. Like, he wants to know what's physically going on. Like, the part of him that played with radios as a kid wants to know what's actually going on. But the part of him that was educated by Karl Popper knows that that's just a bias.
Yeah, it's not entirely satisfying.
Yeah.
Just saying it's a field and something is waving. And I think this is the subtext of what he's trying to say in these lectures.
Yeah, it's definitely a theme that we're going to keep coming up to. Now, what's the importance of this? I wanted to illustrate this for the audience. What's the positive case that Inductica would make for this? Is that we need to think in terms of entities and their relationships and actions with respect to one another. It doesn't mean we don't have to, but that's the goal. It's fine to have a theory that identifies general trends and then makes general statements about what will happen. That's fine, but we have to understand that whenever we have a theory like that, there is all of those general trends are the result of entities acting and relating with one another. So let me give an example. So let's take the theory of relativity. I was having a discussion with an objectivist physicist once, and I told him, well, special relativity is obviously, causally lacking. It doesn't have a causal structure. And he looked at me, he's like, well, what are you talking about? Of course it has a causal structure. And this was strange to me because another objectivist, someone who believed in Ayn Rand's philosophy as I do, they thought it was a causal, like it was actually causal, and I found that interesting. He said, well, how is it that it's causal? And over the course of some discussion, here's basically what his argument amounted to. It was Einstein identified, or I should say re-derived the laws of special relativity from Maxwell's equations. He showed that in order for Maxwell's equations to be true, space and time had to, I'm putting this in quotes because I think that's a wrong way of even thinking about it, but this is the way he thought about it. If Maxwell's equations are true, then space and time have to function in this particular way, including light being measured as the same speed in all reference frames. So so I said, okay, I see. You're saying that Maxwell's equations, in a sense, cause these special relativistic effects. And he said, yes. I said, okay, fine. We can see that Maxwell's equations require these other things to be true. But that's not a cause and effect relationship. A cause and effect relationship is when an entity acts on another entity. It's an understanding of the nature of one entity and how its relationship or action with respect to another entity involves some kind of other bit of identity or some change in identity. We want to understand these things in terms of entity because reality comes down to entities. If we understand the entities and what we're doing, that's what gives us real power to manipulate this stuff. But instead, we have this general trend of fields and this funny aspect of how they work and that they're, Lorentz invariant, and then that leads to a bunch of other effects. But it's not clear what the actual cause and effect relationship is. Now, this wasn't on the docket, But this is related to the way Feynman thinks about mathematics. There's another section, we're not going to be able to look at the part, but Feynman essentially says, he says, I like the Babylonian approach to mathematics, where there's no necessary hierarchy. You just take some of the ideas and you deduce the rest of the mathematical framework from that small set of ideas. You don't think of some things as being more important than others. So, like in the case of special relativity, what's the cause, what's the effect? We have no idea. You can derive the special character of Maxwell's equations from certain assumptions about like symmetries, and you can derive, it's something, I may not be saying that quite right, but it's something like that. And you can derive the aspects of special relativity from Maxwell's equations. So like you could go either way. There's just some facts that necessitate other facts. But you can't go any direction you want when you're thinking about entities acting, because a certain entity with a certain nature requires something else to happen. You can't reverse that process once you actually understand the entities, because at the end of the day, one thing affects another thing. All right, comments, Aviram?
Yes, I agree with that. I don't think that Feynman belongs in the camp of the math worshippers, where they simply think of physics as a formalism that can't be really interpreted. But he is also not insistent on causal reasoning. He's I think, more of a pragmatist about these matters. So
yeah, it's whatever works. See? Yeah. Really quick for our audience, what we mean by pragmatist is specifically, we don't mean that in a positive way. Now, in a broad general way, making practical application your primary standard, that's good. We're not against that. At the end of the day, you need to be successful. And if you aren't successful, it means you're doing something wrong. It means, because at the end of the day, this whole process, the only reason is to get results. So we're not against being practical, but we're against pragmatism, which is a philosophy which says that there are no principles, there are no general facts that you can bring to bear in your quest for success. All you can do is try something, look at the result, and if it didn't work, try something else. And you can see that basically the hypothetico-deductive method is, in a sense, the basic outline of the general pragmatist philosophy applied to physics. So next, we're going to watch another clip that I think is very reflective of his physical attitude, his attitude towards physics. And again, the pragmatism is going to come out here.
Interesting. So if you'll permit me, I'm going to state the law of gravitation in 3 different ways, all of which are exactly equivalent, it turns out. But they sound completely different. 1, there's a forces between the objects as described before, and each object, when it sees the force on it, accelerates or changes its motion at a certain amount per second, as I've described before. The regular way, I call it Newton's law. Now there's a completely different way. That law says that the force depends on something at a finite distance away. See, it has what we call non-local quality. The force on this depends on where that one is over there. Now, you may not like the idea of action at a distance, but it can know what's going on over there. So then there's another way of stating the laws, which are very strange, and it's called the field way of representing the laws. And it's so very hard to explain, but I just want to give you some rough idea of what it's like. And it says different things, completely different things. That there's a number at every point in space. I know it's a number. It's not a mechanism. It's the trouble with this whole physics, that it must be mathematical this way. There's a number at every point in space. Here's a number, and so on. And the number's changing. It changes, rather, when you go from place to place. If an object is placed at one of these points, at somewhere in space, the force on it is in a direction in which that number, I'll call it the name it's given, called a potential, is in a direction in which that potential changes as quick as it can. And the force is proportional to how fast it changes as you move. Newton's laws tell what happened at one time in terms of what happens in another instant. It gives from instant to instant how to work it out. But in space, it leaps from place to place. But this thing is both local in time and also local in space, because it depends only on what's in the neighborhood. And there's another way of representing. That's another way. Now, there's a completely different way. See, there's a difference in the philosophy, in the qualitative ideas involved. You don't like action at a distance. You can get away without it. Now I'll show you one which is philosophically the exact opposite, in which there's no discussion at all about how the thing works its way from place to place, in which the whole thing is an overall statement, as goes as follows. When you have other particles around and you want to know how this one moves from one place to another, you do it as follows. You calculate a certain quantity you invent a possible motion that gets from one given place to some other place that you're interested in a given amount of time. Say it wants to go from here to here in an hour, and you want to know by what route it can get from there to there in an hour, by what curve. So what you do is you calculate a quantity guessing the curve. If you try this curve, you calculate a certain number for this quantity. I don't want to just say what the quantity is, but for those who have heard of these terms, this quantity on this route is the average of the difference between the kinetic and potential energy. Now, if you calculate this quantity for this route, then for another route, you'll get, of course, different numbers for the answer. But there's one route which gives the least possible number for that. And that's the route that the particle takes. Now we're describing the actual motion, the ellipse, by saying something about the whole curve. We have lost the idea of causality, that the particle's here, it sees the pull, it moves to here, it goes. Instead of that, in some grand fashion, it smells all the curves around here, all the possibilities, and decides which one to take. But this is an example of the wide range of beautiful ways of describing nature, and that when people talk that nature must have causality, well, you could talk about it this way. Nature must be stated in terms of a minimum principle. Well, you can talk about it this way. Nature must have a local field. You can do that, and so on. And the question is, which one is right? Now, if these various alternatives are mathematically not exactly equivalent, and if for certain ones there will be different consequences than for others, then that's perfectly all right then, because we have to only to do the experiments to find out which way nature actually chooses to do it. Mostly people come along and they argue philosophically they like this one better than that one, but we have learned from much experience that all intuitions about what nature's going to do philosophically fail. It never works. One just has to work out all the possibilities and just try all the alternatives.
Alrighty, so that's Feynman's view on different formulations of the same physical law. What I found interesting about this is that he's saying, first of all, what I would call a physical theory, he calls a philosophy. So already he's on the view that, like, once you start talking about what I was saying before, entities acting on one another, once you start talking about that, says Feynman, you're now leaving the realm of physics. And this has been something this almost made me quit physics, by the way, because I hated the idea of just doing math to, like, make predictions and that's it. I wanted to understand what was actually going on. And implicitly for years, and then explicitly once I got to graduate school, implicitly for years in undergrad, I was told, like, well, that doesn't matter. Then explicitly, once I started wising up and saying, well, I want to know what's actually going on, they started looking at me like, well, that's not what this is about, James. So, comments on this, Aviram?
Yes. I think that the history of physics suggests an interesting example. If I'm not mistaken, in the 17th century, Fermat said, or rather noticed, that beams of light go through the path of the shortest path possible. I think it's the least path, optical least path, and
that takes the least amount of time, I think.
Yeah, and this was a rather obscure property, because presumably it would cause you to think that light somehow knows which path is the
Yeah.
shortest. But then when
Yeah, I
Maxwell-
remember not even liking that when I was a little kid. I finally know what I didn't like about that now.
Yeah. So when Maxwell's theory was derived, and people understood how to interpret light beams within the structure of the fields that Maxwell was describing in his equations, then they were also able to derive the shortest path property that Fermat's principle is talking about. And so, in a sense, what Feynman says is true, but I'm not sure whether the conclusion follows that you have to be totally unprincipled and pragmatic about the different formalisms. In a sense, eventually you do want to find a hierarchy and explain the more fundamental properties, by means of the more fundamental properties, the ones that are higher up, the ones that are consequential of the more fundamental properties.
Yeah, instead of just whichever one works, that's what we use. Now, you might be thinking that we're making Feynman's point for him. We have this bias towards causal theories that act at specific, with entities acting at specific times. And we haven't like, how do you know that's actually how it works? Well, here's why. Is because reality consists of entities. And the reason things happen is because entities are acting on one another. There aren't any sort of abstract laws that live in reality. Think about that. That would be like we live in a computer simulation and there's like a source code to the universe that the entities are following. No, entities don't follow like abstract laws written in the sky by God or Morpheus or whoever. Like, entities have identities, entities have natures, and they act, and relate to one another in accordance with those natures. So, and here's how that specifically applies to a principle of least action. So a principle of least action, it's this overall principle that the motion of some object has to follow. Or in the case of light, it's the fact that the path it ends up taking always ends up being the path that causes it to minimize its flight time, basically. So that's great. I think, again, that's great, but that doesn't get to the essence of the physical law. So let's think of gravitation. In the case of gravitation, it's like whatever is actually the underlying identity of the gravitational force and how it is propagated, it cannot be action at a distance. First of all, it can't be, I don't think action at a distance is ruled out, but based on what we see, gravity, spreads out spherically. It follows an inverse square law, which means it's spreading out spherically. It spreads out at a finite speed. It's not non-local. It's local. It spreads out and acts at particular locations. Okay, now secondly, how do we know it's not a least action principle? Well, a least action principle involves sort of this summary of all of the actions, but entities act in accordance with their nature at the time that they have it. If there was some kind of least action principle, it would mean that there would have to be some kind of like entity sort of like, conditioning the way that the particle moved at all given times. Well, that does exist. It's called gravity, and it's acting at each particular location during the path. And you'll notice that Feynman even has to rely on the causal view in order to describe what a principle of least action does. He says that it's somehow, the principle of least action somehow, he doesn't even know how. I would like to know how, by the way. I don't know either, but I at least want to find out. How does it... Anyway, he says the principle of least action sniffs out the forces at each given location and then provides like a summary view. Yeah, exactly. That's what it does, which means that the forces, specifically the local forces, which means that the fields are what's actually fundamental. Now, you might be thinking, like, why does this matter? Why does it matter? Like, these are just different formulations. Yeah, technically, maybe it's entities acting at certain locations, but, like, isn't that just, like, abstract stuff that doesn't really matter that much? No, it matters a great deal. Let me give you an example. So, Back during roughly the time of Galileo, there was another physicist named Evangelista Torricelli. I think it was a little after Galileo, actually. But anyway, Torricelli was trying to figure out how vacuum pumps worked. He was pumping air out of a certain container, and when he did that, he found that the vacuum, once you pump the air out, was able to suck water up through a straw or through a pipe. So basically, imagine when you sip on soda through a straw, you're just you're sucking the air out of the straw, and that causes the soda to rise. So Torricelli was trying to figure out how that worked, only it wasn't involving soda. Now, other people's way of thinking about this is they said, it must be some kind of general law that nature abhors a vacuum. So you suck the air out of the straw, and nature abhors a vacuum, so the soda rises to fill the straw. And Torricelli wasn't convinced by that. Instead, what he said is, he said, wait a second. And he said, wait a second, vacuums aren't an entity. You can't talk about the vacuum sucking stuff up, because a vacuum isn't a thing. And this allowed him to realize that when you suck the air out of the straw, you're not sucking the soda up. Instead, what you're doing is you're removing air from the straw, which removes an impediment. What does it remove an impediment on? It removes the impediment on the atmosphere. The atmosphere is pressing down on your soda, and that the atmosphere pressing down on your soda, once you remove the air from the straw, it pushes the soda up into your mouth. So it's not that you're sucking the soda up, it's that you're just removing the impediment for the atmosphere to push the soda into your mouth. And Torricelli couldn't have discovered this without the attitude that these physical laws function by entities acting. He wasn't satisfied with, the general law, nature abhors a vacuum. No. The entity, the atmosphere, pushes the other entity, the soda, up into your mouth. Comments on this, Aviram?
I like this example a lot. I would just be interested in looking up the history and seeing whether it's possible to make the fear of vacuum more rational. Suppose that someone say, no, it's not really that nature knows that a vacuum is going to form there, and so it rushes to close the gap. They might say there is some sort of force of cohesion, some sort of stickiness that makes things not split apart. But prima facie, I think that you made a very interesting connection. Yes, I mean, the idea that nature fears a vacuum does really sound like nature is lazy and he wants to take the path of least resistance. That's unsatisfying. It's a kind of metaphor. It's a kind of image to interpret a certain principle, whether mathematical or qualitative. But eventually you would have to cash it in with a definite kind of explanation.
Yeah, and as long as we think in that metaphor, any of the inferences that will come from thinking in the literal facts of the matter will be hidden to us.
I think that Feynman is noting a legitimate issue here. It is a good thing to have, as a physicist, under your belt, several formalisms or several tools in order to deal with theoretical problems when you want to explain a certain phenomena, for example, or investigate a certain poorly understood one.
This should not be taken as a denouncement of the Lagrangian mechanics or of any kind of theory that is a principle of least action or anything like that. Only to say that we need to be very cognizant of what's physically happening, and a certain theory. And one theory might be very useful, but it doesn't necessarily reflect the physical reality directly. And if it does so only by sniffing out all of those specific physical actions and summarizing them somehow.
Yes. And so one metaphor that I have to think about this is to compare it to the use of different measures of units of measurement. So in atomic physics, people use angstroms, which is a very, very minute measure of length. But in astronomy, they use the astronomical unit, the AU. And you can see there why different tools, let me hide the glow here. You can see there why different tools match different contexts. And my suspicion is that what's going on with the principle of least action is that it's not entirely understood what's the context in which that kind of principle is most useful. But probably what's happening is that least action is the form of the laws of nature which is best suitable for certain kinds of tasks. And we have to ask why. And so in the case of units, you prefer a certain unit because it makes the numbers that you are working with smaller than they would otherwise be. And so there is here an issue of tailoring the right tool to the right problem, but this should not imply a certain disinterest in the right hierarchy of physical principles.
Yes. All right, let's take a look at, now let's talk about Feynman's scientific method. We will watch a clip from him on that.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience.
All right, so that is Feynman's brief statement of the hypothetico-deductive method. I've talked about this in the past. Aviram, what comments do you have on this method?
Yes, I must confess that I find it hard to take this seriously the more I learn about the history of science. I don't know, it's like someone telling me, I just threw a bunch of bricks together and somehow they formed a palace. Science is not formed this way. I don't think that even individual steps in the build-up of scientific knowledge are built this way. I think that scientists work, when they are successful, in tandem with observations, experiments, a certain procedure of asking questions and getting answers and forming new questions against nature. It's not just coming up with a certain theory and then retroactively a guess actually, and then retroactively trying to confirm it. And I think that a mutual friend of ours interviewed the psychologist Edwin Locke, and Locke says, suppose that some biologists in the 16th century tried to explain cancer. I mean, it's inconceivable that someone would do that, and if someone had tried to do that, then the result would be a caricature, because the state of knowledge back then in biology was simply so inadequate that no one could have even guessed an explanation. And so I think that the hypothetical-deductive model that Feynman is catchphrasing here is very mistaken.
Yeah, so that point you raise actually brings us to our next clip, the idea that it's really just a guessing game, and that there's no principles regarding where the guess comes from. So let's hear from Feynman on that.
Because the gravity force is so weak compared to electrical forces. Now I want to concentrate from now on, because I'm a theoretical physicist, I'm more delighted with this end of the problem, as to how do you make the guesses. Now, it's strictly, as I said before, not of any importance where the guess comes from. It's only important that it should agree with experiment, and that it should be definite as definite as possible. What you say then is very...
So we literally see from him here, it doesn't matter where the guess comes from. And I think we're already seeing the fallout from this in particle physics. Now, this is not something I'm well educated in, but Sabine Hasenfelder has made very good arguments from my perspective that in particle physics, they're stalled because they basically just keep entertaining certain guesses, and no guess is any better than any other, so it's just this giant mass of arbitrary guesses that they're testing, and testing these guesses is getting more and more expensive, she is pointing out. And so we can see this isn't a productive, right on the face of it, we can see that this is ineffective method. Now, what we really, in my method, so I've written out a theory of induction, a theory of the scientific method, and the two things that I will do to compare this hypothetico-deductive method against mine is that, first of all, I don't think guessing and checking is the essential method of science. I think the essential method is observing and inferring. You observe certain things directly, and direct observation can be known with certainty. It's that simple. Oh, well, there are certain cases where it's not that simple, where we have to get into illusions and deeper epistemology to understand what aspects, what counts as perception and what we're certain of and what doesn't count as perception. That's a whole issue. But in general, there's a set of observations we can rely on for certainty. And when we wish to go beyond those observations, say when we want to try to understand why chemical reactions work, it's because of the atoms joining into molecules. We can't see atoms joining into molecules, and so what we have to do, we can't look at it harder to see the atoms in molecules. What we have to do is make inferences, deductions, from what we do see in order to get down into that deeper level. And those deductions might sometimes involve a hypothesis, but they don't have to. They can simply be deductions from what is already known. A hypothesis is just a particular kind of question which helps guide your investigation. What direction should we take our investigation? Should we, maybe entertain the hypothesis that matter is made of atoms joining into molecules? And then what can we do to make inferences and to make observations and inferences which might prove that? And the chemists of the late 18th century did in fact do that and did prove that there were atoms and molecules from inferences. Now in this method of mine, a hypothesis is actually pretty hard to formulate. You can't just randomly guess. To call it a hypothesis, it must actually meet certain standards of plausibility. You need evidence in order to frame a hypothesis. It can't be random. And the evidence cannot just be, if this were true, then it would explain the results. That's not good enough. There needs to be outside evidence. So one example I would give is, you can't just say, well, maybe light's a wave. Maybe light's a wave. Well, you need, because that would explain this aspect and that aspect and that aspect. Well, no, you need outside evidence. You need something that actually points to that. So one example would be that light changes direction when it goes from media to media. And that was, at the time, a known property of light. And so since it has that same property, maybe it's the same kind of phenomena. It's not bulletproof, but that's why we call it a hypothesis. That's the kind of reasoning you need. Further comments on the hypothetico-deductive method, Aviram?
No, I think you've made good points. You know that I once told you that I think that maybe we should get rid of the entire idea of hypothesis and just call it suggestions. So you're making suggestions on the basis of the previous conclusions that you've reached, and I don't know. It's an issue of terminology. Maybe we should keep the word. Newton did not like it. I'm not sure how deep his resistance to the concept of a hypothesis is, but it's basically a hypothesis is when you pretend that something which is not proven is true for some purpose, and presumably you can do that in in a permitted kind of way, in a licensed kind of way, in certain contexts.
Yeah. So next I think we're going to see a specific example of how the guessing model it gives us a very impoverished view of the history of physics, which ends up being very important to get right. So let's take a look. Let's take a listen.
Another thing, of course, that one can use to guess is to guess new principles. For instance, in Einstein's gravitation, he guessed, on top of all the other principles, the principle that corresponded to the idea that the forces are always proportional to the masses. He guessed the principle that if you were in an accelerating car, you couldn't tell that from being in a gravitational field. And by adding that principle to all the other principles, was able to deduce correct laws of gravitation.
So he's saying, he's just saying, Einstein guessed the equivalence principle. What are your thoughts on this, Aviram?
Yes, I mean, Feynman has several volumes on physics, so it may be that he's speaking off the cuff here, but I think that that's somewhat imprecise because Newton himself was aware of that equivalence, right? We know that he made experiments with pendula with different material constitutions. So he used pendula made out of wood, made out of marble, made out of metal, and he found that gravity is material insensitive. It induces the same frequency of swinging back and forth no matter what kind of material you put. It's only the mass or the amount of matter present in the pendulum that really, no, not even that. I mean, you cancel the mass. You just, so you just have the length and the free fall acceleration that determines the frequency. And so in a sense, he actually checked to see whether there is no kind of material dependence there. And there's also...
but he extended it to light in a certain sense. He said the way light will behave in your reference frame in a gravitational field is the same as if you were accelerating, which would mean that the light curves from your perspective. So now, the reason I wanted your comment on this is that, to me, this is an utterly insane guess. It's utterly insane. Like, I don't have any idea of how Einstein could have gotten there. And my point isn't to agree with Feynman here, that we just try different things. It's that if we understood what Einstein was actually thinking in order to come up with his equivalence principle, not just the Newtonian one, but the part of it that extends to light, which ends up leading to all of Einstein's insights, we would understand the thinking that led to it, and we would actually understand, that would give us some hints as to like what is physically going on with relativity, instead of just having a formalism that says space and time bend and it's wrong, and at best it just gives us good results. That's what I want to understand, the way Einstein was thinking about it. And unlike a lot of modern physicists today, I don't think that's impossible. I don't think we just have to say, oh, he was a genius, or oh, he was smoking drugs when he came up with the hypothesis. No, he was thinking about it correctly somehow. Otherwise, he couldn't have guessed. He couldn't have a lucky guess. That's what I want to know.
Yeah, I think you can make his inference much more plausible, because as you say, the fact that he extends this to the electromagnetic field is non-trivial. It is actually an addition to the kind of equivalence that was known to Newton and later physicists before Einstein. If I had to guess, I'm not sure about this, I would say that one must remember that we are made, in a sense, out of electromagnetic fields, right? And the pendula are, and everything are. Even things that are presumably mechanical are in fact composed of charged particles. And so maybe what Einstein was realizing is that if electromagnetic action is coupled to gravity in a way that does not mesh nicely with the way that mechanical things couple to it, then some phenomenon is going to pop up and indicate that difference. I'm not sure whether it's helpful, but
I mean, this is the kind of thinking we need in the long run. It may not be helpful, but it's the kind of thing that is, and we need to say things like this. We need to make these kinds of tentative. This is the kind of sparring, Feynman's talking about. Like, you don't know if this is right, but you're thinking about different physical possibilities in general for why it works this way.
And I think that maybe in special relativity there was something similar to that, right? Einstein was, in a sense, saying all of the interactions present in nature are Lorentz covariant. You don't have to go one by one and check. I mean, in a sense, you do want to do that. You do want to identify the different interactions.
Personally, I think in order to check the principle, you have to check the different phenomena, because you have no reason to think that they all,
but you
have the same property.
So, but you do, because if there was one force which was not Lorentz covariant, then it would disrupt the kind of systematic predictions that special relativity predicts. So, for example, there was a person
Then they were already implicitly checked.
Yeah. So, for example, there was this guy Abraham who formed a model of the electron, and his electron was a sphere. It was the filled-up sphere, a ball, and it was rigid. And the mass to velocity ratio that he got, by assuming it's charged, was actually not the relativistic mass to velocity ratio that we know, right? You have m0 over times gamma, the Lorentz gamma. And people initially believed that experiments by Kaufman actually indicate that, it's Abraham's model which is correct and not Einstein and Lorentz's models, because Lorentz also predicted the right model from his more constructive theory. And Einstein said there's a mistake in the experiment. And why was he so cocksure that it's that this way? Because he realized that if there was a fundamental non-covariant law in nature, then it would show up. You could somehow make an experiment that would show non-relativistic effects. But he convinced himself, on the basis of Lorentz's investigations of the Galilean principle of relativity, that the generalization that he realized, the Lorentz covariance, is universal. And so, in a sense, he could have said, yeah, that's not going to happen. It's a mistake in the experiment. And he pulled this trick probably again in general relativity, where he realized that you have to have a very specific kind of coupling between both mechanical masses and fields in order for the principle of equivalence to hold. Otherwise, some sort of a discrepancy would show, and it would violate those observations. That's my take.
So let's go to this next clip from Feynman, which Aviram, you wanted to comment on, and this will sort of show Feynman pointing out a flaw in his own view here, unbeknownst to him.
Position. It turns out that the experimenters have a certain individual character. They like to do experiments even if nobody's guessed yet. So it's very often true that experiments in a region in which people know the theorist doesn't know anything, nobody's guessed yet. For instance, we may have guessed all these laws, but we don't know whether they really work at very high energy, because it's just a good guess that they work at high energy. So experiment says, let's try higher energy. And therefore, experiment produces trouble every once in a while. That is, it produces a discovery that one of the things that we thought of is wrong. So what I would say, if experiment can produce unexpected results, and that starts us guessing again. For instance.
Comments on this, Aviram?
Yes, I think it's an instance of Feynman's intellectual honesty here. In a sense, he is aware that experimentalists, as he said, are making experiments without anyone telling them what to look for, without any guesses. And so he just notes that this happens. But he does not really integrate it with his idea of hypothetical-deductive process. And I just find it funny that, in a sense, Feynman is discovering that philosophy of science is a difficult subject.
Yeah, right. Yeah. It's well, at least we're seeing evidence of that. I don't know if he necessarily sees that. But one thing that we're seeing is the real poverty of this view. The fact that it can't explain all of the aspects of what scientists do that are successful. When these experimenters, quote unquote, go off on their own. Now, they aren't really going off on their own. They're going off based on reasoning from the earlier knowledge. But, to Feynman, the only thing you can do to reason from previous knowledge is to come up with hypotheses and then test them. But that we're seeing here that this just does not cover the gambit of the productive actions scientists actually do. It is a impoverished view. It's an impoverished account of what's really good and really effective about science. So now let's go to another clip, a very important clip on Feynman's view of the scientific process.
Now, you see, of course, that with this method, we can disprove any definite theory. If you have a definite theory or a real guess from which you can really compute consequences which could be compared to experiment, then in principle we can get rid of any theory. We can always prove any definite theory wrong. Notice, however, we never prove it right. Suppose that you invent a good guess, calculate the consequences, and discover that every consequence that you calculate agrees with experiment. The theory is then right? No, it is simply not proved wrong. Because in the future, there could be a wider range of experiments, you can compute a wider range of consequences, and you may discover then that
So what we're seeing here is that you can never prove it right. You can never prove it right because you might continue making observations, and you might come to the view, and you might end up coming across, and I mean, hopefully you will, come across something your theory doesn't describe yet. And that means that your prior theory is wrong. So notice a few things about this. The attitude is we have to write down the law that describes everything about the universe. Not we need to understand certain kinds of entities and their properties and the way those entities form relationships based on those properties. Now, what's the difference? The difference is if you think about it Feynman's ways, you're constantly looking for the source code of the universe, and what do you know? You never find it. You don't consider yourself to have any kind of certainty until you know the entirety of God's thoughts, or something like that. But that's not the way it works. There are no laws just sitting out there in reality, in the source code of the universe, or whatever, stupid crap you want to think about it, or Platonic thought process, to be more specific with my words here. Any kind of Platonic view you want. It isn't a Platonic view. There are entities with properties. You can describe those entities and their properties and the way that they act. And when you come across something that you're not yet able to predict, it just means there's another entity. Or the entities that you are aware of have some property that didn't manifest earlier. And all you have to do is just add to the list. Based on this view, you never gain certainty. Based on this view, you feel like you can never say anything. But the thing is, we say things that are successful all the time. We, shot men to the moon. You can't shoot men to the moon without knowing a great number of things with certainty, without knowing all of the required physical laws required for such a mission with certainty. Now, so we need a better way of thinking about our certainty and uncertainty. We need to be able to say, these are the things that we know, and if something new comes up, then that means it wasn't one of the things we already know. We have certainty about the things we've discovered so far, but we don't know everything yet. That's a much more fruitful way than explaining it in terms of, we just never have certainty, because now you can't differentiate the kinds of things we can actually apply towards technology, and the things we can't yet apply because we literally don't know it yet. There's a strong difference between those, and this attitude wipes that distinction out. Aviram comments on this aspect of the hypothetico-deductive method.
Yes, one way I would summarize what you said is by saying that interference of new factors in a certain regularity is not a refutation of the laws that describe that regularity without those factors. So in a sense, if a new factor introduces itself, the right way of thinking about this is you need to refine your laws. You are not throwing them away. There is no entire overhaul of everything you knew about the theory. And one simple example, for example, is that the concept of a proton is still with us. But we know that the proton is not fundamental, right? So it's made up of quarks, but there's still such a thing as a proton, and we speak about it and we use it in order to explain things. It's an intermediate kind of thing between the more fundamental stuff and atoms and molecules. And it's true that in science, the preservation of older generalizations in the wider ones can be tricky, right? I mean, if you have a force law and you thought it was 1 over r squared, but actually there was a correction of 1 over r to r cubed, then in a sense you have to say, well, this is where the phenomenon is present, this is where it's not, and it's continuous, so you can't really say where the new domain begins in a nice kind of way. But I think that it can be done probably, and you can see it in the proton example. Old knowledge is integrated into the new knowledge, into new generalizations. But I do like to add that Feynman is resisting here a certain strand of thought of the logical empiricists that want to say that physical laws are just restricted kind of generalizations. You are not supposed to extend them beyond the range in which you've tested them. And Feynman is saying, no, I do want to say that everything in the universe gravitates, everything that has mass. Suppose we are in the Newtonian context now. I don't want to say only the things that I've seen so far on Earth, on the solar system, gravitate. I don't know what's happening in Andromeda. And Feynman says, no, that's not science. And he can't really explain it. And because he understands that science has to extrapolate consistently and that Andromeda is part of the extrapolation that applies to Newton's laws, and so you can't just disqualify it arbitrarily, because that must be part of science, Feynman is pushed to the position that, well, I suppose that science is only probable. It's not certain, because I was not in Andromeda and I did not check every stone to see whether it falls in an Earth-like planet over there. But the thing is that you don't have to conclude that, even if you insist that the laws of nature must be extrapolated consistently. I hope I've been clear about this.
You have, and I think what we're seeing here is one more instance of a good scientific soul who has been given bad philosophy to work with, basically.
I mean, he's facing the problem of induction, right? Why can you extrapolate from solar system observations and terrestrial observations that Newton did to things that were inconceivable to Newton? I mean, in the book, Feynman is saying people measured globular clusters surrounding the Milky Way, and they found that they obey the Keplerian law of motion, the Newtonian law of motion, basically. And Newton never knew about these things. But in a sense, the structure of limited phenomena contains enough information for you to conclude much more from those phenomena than you may think at first. And that's the idea of induction. You isolate certain facts that together allow you these extrapolations, and it's a very non-trivial kind of thing, and it's a problem of induction. It's a difficult problem.
Yeah. And we can see that based on the way Feynman thinks, there is no solution to the problem of induction. You can't have certainty because the next thing you see might contradict all of the patterns you found in the past.
Yeah, and let's make it explicit. Let's make it explicit. He is just heavily reliant on Popper, right? I mean, Feynman gives one of Popper's examples, I think, of Adlerian psychology when he speaks about falsifying theories. So, in a sense, Feynman is looking with Popperian eyes on his own science, and the result, which is not surprising, is not very good.
Yeah. And side note to plug my own work, my theory of induction, which is currently available in its rough draft form, if you subscribe to me on Patreon, my theory of induction does give a solution to the problem of induction. Okay, so now let us cover another clip that Feynman, where Feynman discusses his view of the scientific method. Another aspect of his view of the scientific method. I'm pressing the wrong button.
Now, another thing that people often say is that for guessing, two identical theories, here, suppose we have two theories, A and B, which look completely different psychologically, have different ideas in them and so on, but that all the consequences that are computed are exactly the same. They say they even agree with experiments. The point is, though, that the two theories, although they sound different at the beginning, have all consequences the same. It's easy usually to prove that mathematically by doing a little mathematics ahead of time to show that the logic from this one and this one will always be a corresponding consequence. Suppose we have two such theories, how are we going to decide which one is right? No way, not by science. Because they both agree with experiments to the same extent, there's no way to distinguish one from the other. So two theories, although they may have deeply different ideas behind them, may be mathematically identical, and usually people say then in science one doesn't know how to distinguish them, and that's right. However, for psychological reasons, in order to get new theories, these two things are very far from equivalent, because one gives a man different ideas than the other. By putting the theory in a certain kind of framework, you get an idea what to change, which would be something, for instance, in theory A that talks about something that you say, I'll change that idea in here. But to find out what the corresponding thing is you're going to change in here may be very complicated. It may not be a simple idea. In other words, a simple change here makes maybe a very different theory than a simple change there.
Alrighty, so two theories that come out with the same experimental results are just equally scientifically valid. There's no way other than simply the predictions and whether those predictions make correct predictions. There's no way other than that to tell if a theory if one theory is better than the other. So, for example, in the days of Copernicus comes to you with his heliocentric theory, and the medieval astronomers come to you with their billions of epicycles stacked on top of each other. You look at both, and what would Feynman say? He would say, well, the epicycle theory is superior. It makes more accurate predictions. And if we were to talk about how Copernicus's theory might be better, maybe it would only be on this psychological ground that maybe it helps us guess the next theory. But of course, why does it help us guess the next theory? Well, because it's actually more physically correct. And if you've ever taken physics classes, especially if you're a non-physicist, you'll notice that this lack of concern with the physical world and focus just on math, just on making predictions, is ubiquitous. What stood out to you in this, Aviram?
Yes, I think that in the philosophy of science, the issue of equivalent theories and how you decide between them is a very big issue that concerns a lot of people. But I wonder whether a consistent inductivist philosophy of science would really find any difficulty here, because it seems that, at least the way that Feynman puts it, you have a guess and you check it against a very small range of instances, and then someone else has a different guess, and he checks his guess, and you find that both can match the same instances. But as we've said earlier, it's not entirely clear that any real science is done this way. You have a process where you accumulate evidence and you build theories gradually. So in a sense, if you can't decide between two different suggested theories or integrations, you don't proceed. And it's not as though you are forming this hydra of many possibilities and you leave it at that. You strive to narrow down this multiplicity by bringing to bear more evidence. And so maybe I'm thinking this idea of equivalent theories is really a bug of a certain philosophy of science that is basically hypothetico-deductivist.
I do think it's a bug that emerges from the hypothetico-deductive method. I do think that I think if you look at the stretches of scientific history that have been successful, you don't see this kind of thing happening. You see a lot more scientific reasoning rather than just checking conclusions and, epicycles versus heliocentric, they make the same predictions, so what's the difference? No, when science is successful, they're reasoning from causes and actually identifying that difference. And another thing that you'd be able to notice is that the theory of epicycles is just a bunch of curve fitting, which, based on what I know about quantum field theory, there seems to be some evidence that is also a bunch of curve fitting also. But I'll wait to reserve a final opinion on that because I don't know enough about it to say for sure. Here's a prominent place where I think this has influenced the history of science, and that's in quantum mechanics and general relativity. At least in the modern day, I don't know how they were accepted originally, but at least in the modern day, what I see, the justification for these theories that I'm seeing, is that they agree with experiments. It's simply here's a formalism, we're going to show you all the math, and then there's a few perfunctory examples saying this makes correct predictions. Now, the perfunctory examples are perfunctory in the history, in the physics textbooks. In real life, in real life, they do in fact match experiments exhaustively, which is why they are accepted. But that's the problem. Theories like quantum mechanics and general relativity are accepted even though they contradict basic facts of the universe. Quantum mechanics contradicting the law of identity, the fact that things are what they are and you can't have a particle and a wave at the same time. And general relativity being physically vague, talking about how space and time are different for different observers, talking about how space bends without being clear on what space is exactly. And then it has, at the end of the day, a wrong view of what space actually is physically. These sorts of theories are accepted, and when you come up with an alternative, such as the Bohm theory, for those who don't know, is a quantum theory that instead of it being a particle and a wave at the same time, there's basically a wave that pushes a particle around, a completely logical hypothesis that has a shot of being true. But Feynman would come along and say, it makes the same predictions as the quantum theory, so why should we take all the time to do this? Now, why should we take the time to look into your other theory? Now, he's in the next clip, we're going to talk about how he deals with that, actually. He actually has an answer to that question. Why should you deal with some alternate theory when it makes the same predictions? And in general relativity, we also have an alternate, which is Lorentz ether theory, which was developed further by Lajos Janessi. Now, I'm not sure if, Lorentz ether theory has the same amount of predictive power as general relativity, but that could just be because less people have worked on it and they haven't refined the theory as much. But in the meantime, it's a theory that is actually in line with many more of the physical facts that we're aware of. Like, it actually treats spatial relationships as being the same for all observers, and simply measurements are changed by relative motion through the ether. Science is, when we take the view of science that it's about observation and inference, we're able to actually think about the physical cause and effect relationships and think about what is actually going on, instead of, we have a convenient story that is able to consistently predict. You can have a convenient story that makes predictions and is completely wrong. The epicycle theory showed us that. And I think that's exactly what we're staring down the barrel of when it comes to quantum and relativistic theories. Other comments on this, Aviram?
Yes, I think I basically agree. But in a sense, it's important to qualify and say that, in a sense, quantum mechanics is not the bad choice between equivalent theories. It's rather an incomplete theory. As Tim Maudlin calls it, it's a recipe in a sense.
Yeah.
It gives you a procedure for calculating things.
Yeah.
But the physical interpretation itself is unclear. Now, it's true that some people insist that quantum mechanics as it is already contains an interpretation, and usually they appeal to the Copenhagen interpretation, which is a vague form of mysticism. But that's also just a defective theory. It's not a plausibly good interpretation that is being competed by other ones. It's just a essentially flawed interpretation.
Yeah, I haven't thought about this in a while, but I tend to lean towards the view that unless you state that your theory is nothing more than a recipe and a model for making predictions and nothing more, unless that's explicitly stated, then a physical interpretation, I hate that phrase, by the way, a physical meaning of a theory is unavoidable. And so as a result, when I say quantum mechanics, I don't differentiate that from the Copenhagen interpretation. I don't think I think a theory involves an interpretation. Because a theory involves a statement about the physical world and its actual constitution. Now, you can take the quantum Copenhagen theory, strip it of all the Kantian Bohr nonsense, the Kant/Bohr nonsense, and just say this is just a formal theory. You can do that, but I don't know if I've seen it done really, because you have to really strip it down. You have to strip the theory of a lot of things in order to commit to that position. So, for example, consider energy eigenvalues. We're getting into the weeds a little bit, but consider the energy eigenvalues of a function. Is that the actual energy? Is that the actual energy of the system? Or is it some number you wrote down in order to make certain kinds of predictions for energy outcomes? Now, I think there's evidence that it's the latter only, that it's not the actual energy. Here's why. Think of tunneling. In quantum tunneling, a particle gets to like a position it isn't supposed to be able to get to based on the amount of energy it allegedly has. Isn't that when you measure a particle to have tunneled to a certain like potential location, when you measure a particle to get to tunnel to a certain location with a certain potential energy, that's an energy measurement, isn't it? At least so. This is only a half-cocked thinking here, but like I think you really like my only point here is you really have to question if you're willing to say, oh, it's just a way of coming up with a recipe for making predictions, then you really have to do a lot of work to strip any physical, you get what I'm saying, any physical content from the theory and say, this is the only thing. It only makes these predictions and the rest is non-physical. It's just a procedure. It sounds like you have a lot to say.
I agree with what you've said. But it's like asking, is a half-baked cake baked or unbaked? The answer is it's half-baked. It's an intermediate state. And I agree.
But which parts of the cake are baked and which parts of the cake are unbaked? We don't know.
I mean, if you look at people who are using quantum mechanics daily, in solid state physics, in quantum optics, and in related areas, they develop intuitions about real physical systems. The principles of quantum mechanics speak to them in a very meaningful kind of way. And eventually, if you ask them, but what measurement is, and what is superposition, etc., then they get stuck. But in many, many accounts, they do use quantum mechanics in a very informed kind of way. It's not just mindless calculations. And so and so I would say
I don't think I've ever. I think that's important to say, because with sort of the cavalier way I'm saying some of this stuff, it might imply the opposite of what you just said. That I think these people just don't know what they're doing. They're ineffective. Like, they're not. They're very effective at some things, but the lack of clarity on these issues is preventing further progress in certain ways. But I'm not sure how that pertains to my point, which was simply that we don't know which parts of this theory are physical and which aren't. So if we were to truly do what you're talking about, to really just say, this is just a model for making predictions, I think what we would have to do is we would have to be very clear about which parts of the theory are physical, that is just the predictions, and which parts are just a model, are just purely a hypothetical fabrication for producing those predictions. So for example, if you were to conduct such a stripping of the theory of epicycles, what you would have to do is you'd have to say the final position of each planet that we calculate, that part's physical. Everything else is a fiction. The spiraling, we don't know if it spirals. The individual epicycles, we don't know if these epicycles exist, etc. All of the mechanics of the theory, you'd have to be very clear. We don't know if that's actually happening, and it probably isn't, right? But this model makes correct predictions, and those predictions are physical. The stars really do appear at those locations at those times. And doing that to quantum mechanics would involve a lot of work that hasn't been done. Because when I teach quantum mechanics, I constantly find myself tripping over, wait, which part of this is just meant to make predictions, and which part of this is actually physical and we know that it's real? I constantly trip over that because as I teach quantum mechanics, I'm dedicated to not misinforming the student. At the same time, I have to teach them the ordinary quantum mechanics theory because I don't want them to fail their class, so I don't spend too much time on like a Bohm theory or anything like that. I teach them the normal theory, but I insist this is just a way of making predictions. It's wrong. It's a flawed theory. So I find, and the reason I know that it hasn't been stripped yet is because when I teach it, I'm constantly tripping over myself trying to strip it. I'm not able to do it as I teach it.
Yeah, I think that many share this frustration because it feels as though this theory has a lot of definite content, but you can't articulate it fully. You can't really satisfy all of the points that you want to understand, like superposition and measurements, etc. So I agree with you, and it's a in a sense, it was a comment against myself when I quoted the modeling saying it's a recipe. it's not just a recipe. There
Right.
is more content than that. But the thing is, it's an incomplete theory. At least, I mean, it's not necessarily incomplete in the sense that you have to add Bohmian corpuscles or you have to add dynamical collapse. Maybe there is something else that you need to add, or maybe you don't need to add anything, as some people in the Everett interpretation say. But you have to add some understanding, some additional clarity that is missing. But some insight is already there, right? I mean, I don't know, the stability of matter. Quantum mechanics seems to be telling us why matter is stable, right? I mean, people were not able to explain molecules before it. And so quantum mechanics tells you, yeah, you're going to have bound states of the atoms in the periodic table. That's that's very physical. But you can't go all the way, right? You can't actually cash out the prediction of molecules in terms of individual pieces of matter undergoing individual processes and motions. That's missing, and no one would disagree with you, I think. I mean,
they were able to explain things that were, yeah.
The people with the Copenhagen.
It sounds like they were able to. It sounds like they were able to explain things that were lower in the hierarchy, such as the structure of atoms and molecules, but they weren't able to explain things that are higher in the hierarchy. You know, the underlying causes. So they're saying, how do electrons behave? Well, they behave in this certain way. We're not really sure how, but we know some things about how they behave, and here's a way to model it. Okay, as a result of that, we know how molecules form. But we can't, but the question, well, what does it mean for the electron to behave in that way? What is it doing? Yeah. I think we've closed ourselves off to that question so long as we focus on the existing framework.
That's a fair position to have, yes.
All right. Well, let's take a look at the next clip. So this is what I was promising you guys earlier. This is Feynman coming face to face with what happens when someone has an alternate theory that is apparently equivalent to the mainstream theory. What do you do in situations like that? So let's take a look at what he has to say.
So the philosophical ideas between Newton's theory of gravitation and Einstein's theory of gravitation are enormous. The differences, rather, are enormous. What are these philosophies? These philosophies are really tricky ways to compute consequences quickly. A philosophy, which is sometimes called an understanding of the law, is simply a way that a person holds the laws in his mind so as to guess quickly at consequences. Some people have said, and it's true, for instance, in the case of Maxwell's equations and other equations, never mind the philosophy, never mind anything of this kind, just guess the equations. The problem is only to compute the answers so that they agree with experiment, and is not necessary to have a philosophy or argue or worries about the equation.
So to paraphrase Einstein here, if that's what physics involved, I would rather be a garbage man. He said a shoe repairman, but I would rather be, I don't know, pick the worst job you want. I'd rather do that than this bullshit.
That's true, in a sense, yes and no. It's good in the sense you may be, if you only guess the equation, you're not prejudicing yourself and you'll guess better. On the other hand, maybe the philosophy helps you to guess. Very hard to say. For those people who insist, however, that the only thing that's important is that the theory agrees with experiment, I would like to make an imaginary discussion between a Mayan astronomer and his students. The Mayans were able to calculate with great precision the predictions, for example, for eclipses and the position of the moon in the sky, the position of Venus, and so on. However, it was all done by arithmetic. You count a certain numbers, you subtract some numbers, and so on. There was no discussion of what the moon was. There wasn't even a discussion of the idea that it went around. There was only calculate the time when there would be an eclipse or the time when it would rise, the full moon, and when it would rise, half moon, and so on. Just calculated only. Suppose that a young man went to the astronomer and said, I have an idea. Maybe those things are going around, and there are balls of rocks, like rocks out there. We could calculate how they move in a completely different way than just calculate what time they appear in the sky and so on. So of course, the Mayan astronomer would say, yes. How accurate can you predict eclipses? He said, I haven't developed the thing very far. He says, but we can calculate eclipses more accurately than you can with your model, and so you must not pay any attention to this. The mathematical scheme is better. And there's a very strong tendency of people to say against some idea, if someone comes up with an idea and says, let's suppose the world is this way, and you say to him, well, what would you get for the answer for such and such a problem? And he says, I haven't developed it far enough. And you say, well,
so yeah, that's exactly what happened to Copernicus. For a long time, Copernicus's model was not as accurate as the medieval epicycle model. The biggest thing that jumps out to me here is that philosophies, as he calls them, which really mean, he calls them philosophies is to kind of derogate them. But what he really means by philosophies here is physical meaning behind the equations. They're just mental shortcuts. They're just these shorthands to, help you remember which calculation to make at what time. No, this is a complete reversal. The purpose of scientific knowledge is to first understand the cause and effect relationships, and math only comes in to elaborate on the properties of those cause and effect relationships. You need to understand what cause and effect relationships you're even talking about before the math means anything. And this is, if you've ever been in a physics class and just thought like, oh my god, this is just a bunch of math that doesn't mean anything. That is just an enormous tragedy that comes from this way of viewing physics, is that it's now taught in a way, physics is now taught in a way that is unphysical. That is not the way physics has to be. That is an artifact of the way you're being taught. So if you're a physics major and you went into physics class and you now hate physics because of all of the math, it's not the math's fault. It's not physics' fault. Math is great. Like, it's just that it's being improperly prioritized. So tell me what you think is going on here. Is Feynman sort of catching on to a problem with his own view here?
I think again
because he brings up the Mayan astronomer and he kind of acknowledges like, well, he kind of is acknowledging like there's a problem with my own view here. We can't just go by the results of the results of the predictions, because what about this Mayan astronomer who's basically Copernicus? And then he doesn't have a good argument under Feynman's philosophy. So what do you think's going on here, Aviram?
It seems that he's tempted by the instrumentalist approach. Math is just an instrument for making very concrete predictions. It has no physical insight. He's tempted by it, but then again, he has to acknowledge that by thinking of the causal story, you get better results. And this is where Feynman is really sensitive about things. He is a pragmatist, and so he is monitoring for success. And if you show him, well, this guy is thinking about explanations and the meaning of the math, and he gets right answers, Feynman says, okay, then sometimes I'll do it his way. And so in a sense, his pragmatism prevents him.
Yeah, he is doing that.
And as I told you before, I think that in other places in the book or in the lectures themselves, you can see that the way that Feynman integrates things is in light of a pragmatist philosophy, a pragmatist way of thinking. And so I think this is one more instance of this.
So it's very often true that experiments in a region in which people know the theorist doesn't know anything, nobody's guessed yet. For instance, we may have guessed all these laws, but we don't know whether they really work at very high energy because it's just a good guess that they work at high energy. So experiment says, let's try higher energy. And therefore, experiment produces trouble every once in a while. That is, it produces a discovery that one of the things that we thought of is wrong. So what I would say, if experiment can produce unexpected results, and that starts us guessing again. For instance, an unexpected result is the mu meson and its neutrino, which was not guessed at by anybody, whatever, before it was discovered, and still nobody as any method of guessing by which this is a natural thing.
So this, so what he's describing a certain process by which science can progress, and I think this is a good process, which is basically you have certain principles. I'm interpreting him generously here. You have certain principles, you apply them universally, then you get yourself into some kind of situation where you find the principle doesn't apply. And these situations are not, contrary to the way it works in the show Three Body Problem, where everyone starts panicking because the laws of science are violated. Instead of this being cause for panic, this is an opportunity because it means something new is happening and you get to discover new principles. And Feynman agrees with this, incidentally. Feynman sees these as an opportunity. He frames them as your theory being wrong, which is unfortunate, but he has this proper, healthy attitude towards the new and exciting. That's just his sense of life shining through. Here's the problem, though. This isn't the only way science progresses. And there's an entirely different avenue by which science progresses, at least one other, which is let's say you have a certain set of facts and there are no exceptions to your principles, and you have principles which are able to make correct predictions about that set of facts, and you don't notice any inconsistencies, but you can still dig deeper. So, for example, there was a point during Lavoisier's day. Lavoisier was basically the Newton of chemistry back in the 1700s. During Lavoisier's day, it was pretty well understood. A lot of chemical reactions were pretty well understood. Oxygen, hydrogen, when you explode them together, it makes water. All of these different chemical reactions were understood. And I think they were finding exceptions here and there and interesting edge cases. But by and large, but even if they weren't, there would still be an opportunity to ask the next step. And that's exactly what Lavoisier did. He said, why is it that chemicals combine in the way that they do? And to do this, and in order to answer this question, Lavoisier made the distinction between elements and compounds, which was a key step towards understanding atoms and molecules. And this kind of question would not have been raised if we used Feynman's method, if we used the hypothetico-deductive method, because we'd be in this situation where, well, we understand what's going on so far. We understand what's going on so far, or rather, we don't understand what's going on so far, but we're able to make correct predictions about what's going on so far. Our theory is consistent with that. So we're good. There's nothing really new to explore. And that's exactly the situation we're in right now. We're in a situation where you have formalisms, which are excellent at making predictions in the set of phenomena which are currently understood. We have GR, which is able to understand gravity. We have quantum mechanics, which is able to understand much of what we know at the microscopic realm. But the way to move forward is just the way Lavoisier did, is to take the next step deeper. Well, what really is gravity? What does it mean for space-time to bend? Is that even the right way to think about it? What are these quantum waves? What are they a wave of? These are the questions that we can ask to go deeper, just like Lavoisier did. And because we now accept this method that Feynman is talking about, that's not an avenue of questions that's open to us. Because our theories are just fine at making predictions, and apparently, as long as we can do that, we're completely satisfied. What are your thoughts on this, Aviram?
I think that Feynman is acknowledging what you're saying, right? He's saying the experimentalists are looking for ways in order to make trouble for us theoreticians. So in a sense, he's acknowledging that there is...
Yeah, but it's a poor man's way of acknowledging it. He's not understanding the kind of question you ask to make trouble for him. He's just saying, oh, they just tried in a different energy range. Yeah, but why did they try it in a different energy range? Why did they think that energy range would make a difference? I mean, based on what I know, I see no reason why a different energy range would make a difference. That's because of my lack of understanding. But ideally, you have hypotheses about the underlying nature of how this stuff works, and then that's what directs your experiments. One example of this. The way Maxwell discovered the displacement current that's the missing term in Maxwell's equation. A changing electric field causes a swirling magnetic field. That's displacement. That's displacement current. The way Maxwell discovered that was by coming up with a model of the ether, a mechanical model of the ether that accounted for all of the electromagnetic effects understood at that time, and then hypothesizing that by the nature of that mechanism, it would have to do this extra thing. That's the and then Hertz went out and did the experiments to confirm it. So this is you're right, Aviram. He is acknowledging it, especially because I think he has practical experience as an actual physicist. But he's trying to smash that into the formalism he was taught from Popper.
I agree with that.
Do you know how specifically Feynman was influenced by Popper? Did he know Popper personally, or was he influenced by his book when he was young? How was he exposed to this?
That's an interesting question. I mean, Popper was alive up until 1982, something like maybe even the 90s. I think that he was.
Yeah.
He was. But back then in the 60s and 50s, he was a big shot, and physicists love him to this day for some reason. Something about his philosophy of science just clicks with them. But just to reinforce your point, I think that yes, as inductivists, we may be able to explain better what's going on here. So suppose, just to give another example, people are using Rutherford's method in order to understand the structure of an atom, and then they discover, actually it was Rutherford himself, that there's a nucleus in the atom. There's a high density little thing in it in the middle, and so they say, okay, let's study the atom, and we will go back to the nucleus later. And you see that quantum physics and atomic physics is focusing on calculating atomic spectra, right? But eventually, they want to understand also the nucleus, because the nucleus is also a thing which they need to understand. But at that point, they don't have any theory about the nucleus. So they are just shooting things at the atom and looking to see what comes out. The scattering and the production of new particles as they discovered. And at that stage, really, you're not trying to cause trouble to the theorist, and you're not trying to confirm a certain hypothesis. You're just looking for more data. You're just like Columbus. You take your ship and you sail, and you want to see what's out there, and you don't have any prior theoretical ideas, with the exception of knowledge that you already have. I mean, you do bring to bear knowledge about optics and material strength when you actually build experiments for nuclear physics. But that's not a hypothesis. That's just knowledge that you validated previously before you approached this new investigation.
The model for understanding that process is not, research, hypothesis, test. The model is, prior, you have your prior knowledge from earlier in the science. So, I guess you could call that research. And then you don't necessarily have a hypothesis. There's just another thing you look at. You're motivated to make a new observation, and sometimes that observation is guided by a hypothesis, but that is only one of many ways that science can proceed. You can just try a new thing to see, we haven't tried this yet. Does electricity pass through a certain material or not? Does it pass through this material? Does it pass through this material? It's like, okay, well, did you have a hypothesis there? No, you're just trying things to see what the nature of these different materials are and how it interacts with electricity.
Yeah, I think that a lot of people equivocate between hypotheses and the products of previous induction. So for them, if you assume anything, if you're not a baby, then you are a hypothetical-deductivist. And so I assume previous knowledge. I don't assume what I need to discover and or prove. And when I do hazard a suggestion, it should be small and well motivated and quickly compared with observations.
Right. Now, let's produce some ending notes. To end this conversation. Aviram, what are your main takeaways from seeing these clips overall?
I'm surprised at how common Feynman's ideas still are in the way that people think about science. Although Popper is not that popular among philosophers of science, it seems that the specific kind of mindset that Feynman has is still very much prevalent. And I think, as you've mentioned Sabina Rosenfelder, I mean, it's no surprise that physics is facing the problems that she articulates, because in a sense they repeat the same mistakes.
Yeah, that's a really good point. Like, a lot of the things Sabine is bringing up are the symptoms of this flawed method. And what's interesting is that she still 90% participates in it. She's able to point out a lot of its bad effects, but she's in this same faulty Popperian tradition. When you hear her, she's like, well, the only thing that matters is that we get the right result to experiment. She says stuff like that all the time, despite seeing the consequences.
It's even worse. When she's called to justify her interest in superdeterminism, she actually says things like, "I like it. It's nice." And whenever and Feynman actually has, I'm not sure whether I will be able to find it, but he has lines where he's just saying, "It's nice. I like it. It suits me." He says some people like causal stuff, and some people like the mathematical stuff, and some people just like to predict results, and everyone has its own taste. And this flips me out because it's a byproduct of hypothetical deductivism, right? In the context of discovery, you are free to do whatever you like. So just choose hypotheses on the basis of your psychological dispositions. So in a sense, she's not free from. I mean, it's not a video about her, so we maybe should change the subject. So. But you're definitely right. It's out there yet still.
Yeah. So as my final note, I would like to just make 2 overall points to summarize what you guys have seen in this discussion. We've really emphasized 2 major things. Number 1 is the inductive method over the hypothetico-deductive method, which is the process of making observations, gathering that knowledge that can be known with certainty because it's seen from observation, using that knowledge to make inferences towards things you cannot directly observe, then using that further knowledge to make even further observations deeper into nature. And that further knowledge allows you to make experiments you never would have been able to think of before. And that gives you even more directly perceivable knowledge, which you can then make more inferences from to produce even greater and greater knowledge. That is the inductive progression, whereas the hypothetico-deductive approach is this guess and check methodology that we've been hearing from Feynman. And we really think at Inductico, the way to get a big part of the way physics can make progress is by changing this really flawed methodology towards the inductive model instead of the hypothetico-deductive model. The second big point that I wanted to emphasize, positive point that we want to take away from this discussion, is the emphasis on physical thinking and physical inference above mere modeling. The idea that we actually can know the physical identity of these physical facts out there. Now, that doesn't mean that everything is mechanical. I'm going to do a whole nother show about people like Bill Gates. You ever heard of Bill Gates, the Donald Trump of physics? He's this guy who literally looks like Donald Trump. Yeah, I mean, the similarity, I don't want to be rude to him. Like, the similarities end there. He kind of looks and talks like Donald Trump. And he criticizes modern physics in a lot of ways that are very appropriate, but he is overly mechanical from what I've seen to him. Now, when I say that it's physical, I don't mean it's mechanical. I don't mean that, like, the ether is really made of little balls and wheels, like, rotating against one another. Maxwell didn't even think that that's literally what was going on. The point is that the physical world, whatever its constitution, is made of physical entities acting in accordance with their nature. And we need to, and real understanding means thinking about these physical entities, not dismissing them as just philosophies that are just window dressings to help us guess the next mathematical equation. So those are the two positive points I really wanted to emphasize. So Aviram, thank you for joining me for this discussion. I hope we have a lot more. Yeah, you're very welcome. And so to support Inductica, just go to patreon.com/Inductica, make a donation. If you make a donation of $5 a month, then you get access to a lot of exclusive content, including a inductive development of physics, a 34-hour inductive development of physics. So I encourage you to visit Patreon for that. What else? You can follow me on Twitter and Facebook to see when the next videos are going to come out. Please like and subscribe this video. And I hope to see you guys in another few weeks when we are going to be starting rigorous inductions of math, building up our scientific knowledge all the way from cavemen counting rocks all the way to quantum mechanics and beyond. So I hope you'll join me as this journey continues. Thanks for joining us.